Understanding variation is key to interpret the value stream behavior. Not all variation is the same. We need to distinguish between random variation and special cause due to one or several factors. This we can do with the help of statistical process control. When we want to cook a turkey, there are a number of factors which will affect the outcome. The raw material, the breeding of the turkey, the equipment used, the method, the manpower, skills, the metrics. All these are possible causes of process variation. Every process has variation. Some causes of variation may be identified and acted upon. We can use two metrics for variation which complement each other, a run chart and a frequency distribution histogram. We will now use an Excel file to simulate the throwing of 4 dice and adding the outcomes. An histogram and a run chart will automatically be built. Scan this QR code to download this Excel file to your PC from OneDrive. Close all Excel sheets before you open this one and enable macros. Open the dice sheet, press reset, and keep on pressing F9 to throw the 4 dice. Each outcome is independent of the previous one. This defies some widely accepted fallacies among gamblers. If a number won last year, it has less chance than other numbers this year. After 3 consecutive reds, there is more chance of getting a black. We can't see any significant trends up or down. Therefore, this is a stable process. It continues to behave the same way. It is stable in spite of its large variation. This is what we would expect, since we have not changed the way we throw the dice. So the process will continue to behave this way while we do so. We did nothing different to obtain the high or the low values. The outcomes are purely random. Motivation will only produce frustration of the employee and no improvement in this case. The outcome in this case is purely random, and the employee running the process has no way to improve it. Some managers in a case like this may get the impression that the variation is a consequence of their own positive or negative employee motivation actions. But we know in this case it has nothing to do with it. Yes, the histogram is close to normal. This is a stable process following a normal distribution with average 14 and a standard deviation of around 3. Throwing 4 dice, there is only one combination that gives a sum of 4, all ones. But there are many combinations that give a sum of 14. The distribution of sums of 4 throws follows a normal distribution in spite of the distribution of single values following a uniform distribution. This is the central limit theorem. Throwing one single die, the distribution will be uniform. All outcomes have the same probability. It is not possible to predict any one outcome. Yes, in this case of a stable process, we can know the frequency of each outcome with a histogram for a large number of throws. Yes, two different run charts can produce the same histogram. The histogram cannot tell us if the process is stable. This can be done with a run chart. Stability doesn't necessarily mean that the process is okay. It just means that the process is neither improving nor getting worse. Let's now analyze another process. Open Shift Alt, press Reset, and keep pressing F9 to run the process. Looking at the run chart, we can clearly notice that this process has a significant upward trend. Therefore, it is not a stable process. Its average is shifting up. It is very unlikely that this data comes from throwing 4 dice, apart from the values above 24, which would be impossible. In this case of an unstable process, as shown by the run chart, the histogram is completely misleading if we want to predict the process behavior. The histogram predicts that values below 15 have a certain probability of occurring, but from the run chart, we see that this is very unlikely. If the process is not stable, as shown by the run chart, the histogram is useless to predict future behavior. We can conclude that the run chart and the histogram are both necessary and they complement each other. First, we must check that the process is stable with the run chart, and only if it is, we can use the histogram to characterize the process behavior. The question is, how do we know if the process is stable, apart from just our impression? What is a significant trend? The answer is to use an SPC chart. Open Shift Alt SPC. The green and red dots indicate a significant upward trend. This confirms this is not a stable process. Open Shift Defects. This represents the number of defects produced by the different operators during 1 week. Supposing you are the manager, based on these results, answer the following questions on the actions you would take. What management actions would you take? Talk to Amparo to remind her of a zero defect commitment with the customer. Congratulate Fernando for his results and maybe give him a prize. Ask the process engineer to explain why Mondays produce more defects than Fridays. Tell operators that anyone producing above 8% weekly average defects will be penalized. If you have decided on any of those actions, you are wrong. In fact, they may be counterproductive. This would be an example of overreaction on the part of management due to a lack of understanding of process variation. To see this, just press F9 to simulate another week with this same process. Your opinion on who is best or worst may change. To know if there is a significant difference among the employees or among the days of the week, we do a two-factor ANOVA with Excel data analysis, and both p-values above 0.05 confirm that there is no significant difference. Open Sheet Control and press Reset. You are responsible to control a machine to ensure that the deviation from target is 0 in every run. You can set the adjustment value, positive or negative, to be applied to the next run. Set the adjustment and press F9 for the next run. Repeat for 25 runs. Don't worry, you have been given an impossible task. With our adjustments, we made the process much worse, increasing variation, standard deviation, to 38. With no adjustments, the standard deviation would have been much lower, 14. We see that the process has random variation and its average deviation is well centered in 0. This means we can't improve it with our adjustments. In fact, we will increase the variation and make it worse. In this case, the operator has been given an impossible task. Someone is shooting at a target, and based on the deviation of the impacts, he adjusts the gun sight after each shot. The result has been an increase of the dispersion of the impacts. Therefore, the adjustments have made the process worse. Adjusting the sight after each shot was not a good idea. So let's fire 5 shots without adjustments to decide if adjustment is required. There is a large dispersion, but well centered. This means that adjusting the sight will not improve the results. What I need is to learn how to shoot. In this case, we can improve by adjusting the sight. If you drop a live frog in boiling water, it will immediately jump out to save its life. But if you put it in a pot of cold water and heat it slowly enough, the frog will eventually pass out without any reaction. Many companies have fallen into this trap. A big disaster generates a quick and effective response, and the company recovers. But the slow degradation of their KPIs, such as customer sat or delays, pass undetected until it is too late. Statistical process control will help us detect when a significant change has taken place in a process and corrective action is required. We will use an example of the process of controlling our own body weight. Download this Excel file from OneDrive onto your PC. You can decide the frequency of your data collection. In this example, I have collected it daily. It is important to collect it the same moment, more or less, each day. You can either have your Excel file in your smartphone or in the cloud, Google Drive or OneDrive. Open the sheet weight in the Excel file. To enter the date in column A, we will use data validation. In cell X1, we have the formula equal to now open close brackets, which will produce the current timestamp every time the sheet is updated. We have defined the data validation for the whole column A, so by clicking on the arrow in the cell, the timestamp from cell X1 will be presented. So just click on the timestamp and it will be entered in the cell. The average of all values, X bar, is the center line in the graph, and sigma is the standard deviation of all values. The most obvious trend is a value above the upper control limit, upward trend, or a value below the lower control limit, downward trend. We define zone A as the area 2 sigmas beyond the center line. 2 out of 3 consecutive values in zone A is an indication of out of control. Zone B is the area 1 sigma beyond the center line. 4 out of 5 consecutive values in zone B is an indication of out of control. 7 consecutive points on the same side of the center line is an indication of out of control. 7 consecutive points increasing or decreasing is an indication of out of control. These are commonly used rules to detect statistically significant trends. Green indicates downward trend and red upward. You can see the description of the symptoms by placing the cursor on top of them. If the weight value is black, it means stability. Green means significant weight decrease, and red, significant weight increase. The numbers on the right indicate which rule or rules have detected the trend. You can see a significant decrease from March to April. This is statistically significant. You must decide whether a 2 kilo decrease is enough. In sheet weight, meant to be used from a smartphone, there is no graphic. We just show alerts of significant trends. In sheet SPC, you can find an SPC chart for individuals you can use as an alternative.